In this section, we're going to take a look at higher order derivatives, specifically the second derivative. So we've got a function, we take its derivative. We take that derivative, we take the derivative of the derivative. That's what a second derivative is. And it gives us one of two things. It gives us acceleration, and it will also help us talk about concavity, which we'll talk about what that all means once we get going here. So let's go ahead and here we go. Let's take a look at the second derivative, the meaning of acceleration. So if we've got a function that is position over time, or at a particular time, how far something is at a given time, when we take its derivative, what that gives us is the speed or the velocity, so v of t, how fast it's going. Velocity is speed with direction. It's also the direction, whether it's going up or down, left or right, all that kind of stuff. When we take the derivative of velocity, we get acceleration. And that's whether we're speeding up or slowing down. We're still moving. Okay, so that's the idea of acceleration. And so when we think of acceleration, it is the second derivative of the position function. So we get position, again, position over time. Take its derivative. That first derivative is speed, velocity, and then take that derivative, and what we have is acceleration. I guess that's with the 1L, acceleration. Okay, there we go. And so let's look at some examples. So first of all, a second derivative. What is that? Well, the second derivative is you take a function, you take its derivative, and then if you can take the derivative of the derivative, that's the second derivative. So notice we use two little primes for the second derivative. That's one way of writing the second derivative. And if it exists, then we have something that's twice derivatable. Now, something like a linear equation, once you take its derivative, you've got a constant. You take that derivative, you get 0 all the time. So x squareds, you take that derivative, you got a linear, you take the derivative of that, you get a constant. So we'll look at a few of those examples. So here's a quick one. Here's an x cubed as our function. We use the derivative rules that we've been using to take its derivative. The 3 comes down in front. Subtract 1 from the exponent, there's the square. This one, the 1 comes down in front, so you just have the first derivative is 3x squared minus 1. When we take the second derivative, what we're doing is we're taking the derivative of the derivative function. So the 2 comes down, 2 times 3 is 6. 2 minus 1, you subtract from the exponent, that's x to the 1. So this is our second derivative. And if you plug in a value, say -2 for x, we find that the second derivative at -2 is -12. So if this was a speed, if this first equation, our first formula, first function was a position function, this would be velocity, and this would be acceleration. So what it would tell us is that at -2, whatever that was, it was slowing down. Okay. I don't know what -2 time would be, but here's another one looking specifically. So we get this position function is t cubed plus 2t squared is the car's velocity. We take the first derivative. That's not the velocity. It's a position function. The car's velocity is the first derivative. So we take that, you get the 3 coming down, 3t squared plus 4t. And then when we take the second derivative, that's when we get acceleration. And you'll see that that is 2 times 3 is 6, 6t plus 4. So this is going to give us the acceleration at any given time. And you will have problems in the homework where you're just asked to find the second derivative. Take the derivative, and take the derivative again. So that's pretty straightforward. There will be times when they'll ask you about acceleration. They won't mention derivative at all. They'll tell you we've got the position function here. What's the acceleration? You've got to know that that's the second derivative. There's some additional notation that comes along with the second derivative. We looked at the one with the two primes. That's one way to write it. Another way is, so here's the two primes, is this notation here, d2f dx squared. So that they kind of show you it's the derivative. So we've been using this sometimes for the first derivative. So we're taking the derivative of the derivative. So you can tell that with these little, it looks like an exponent. It's really not. It's an indicator that this is a second derivative. Okay. If we're using a function in terms of y, it could be d2y dx squared. I'm not really sure how you say those, but when you see the square, what looks like a square, it's just a second derivative. So we'll just look at this and we say, what is this? This is just the second derivative. We can also use this notation, or we could use y double prime. I kind of like this, but then at the same time, it's sometimes difficult to see it. So you'll see both of these notations in the homework. That's the main thing is, what does this mean? It means second derivative. Again, sometimes you're just given the function, ask for the second derivative. To get here, we needed to take the first derivative, but they didn't ask us for it. So there'll be times where, again, we don't put that in as the answer for the homework because they never asked for the second derivative. For the first derivative, right? This would be dy dx, but we had to figure that out so that we can get to the second derivative. And we'll look at this one example because the acceleration due to gravity. Okay, so this is a position function. It's a particle that's law of physics. The height of an object near the surface of Earth falling in a vacuum from an initial rest position so many feet above the ground under the influence of gravity. So you're in a really tall building, you drop something off, it doesn't matter its weight, but this tells us this is how the position's going to change, right? T seconds. Find its acceleration. The first thing we have to find is the velocity. We can't directly jump to the acceleration. What we do is we go to the velocity first, which is the first derivative. And 2 times 16 is 32, actually negative 32, right? Because of the negative t. So this is the first derivative. To get to acceleration, we'll take the second derivative, and hopefully you can see that's just going to be 1 times negative 32. That acceleration is simply going to be negative 32. It's a constant. So velocity will change, the actual speed changes, but acceleration doesn't. And again, this is in a vacuum. The thing is we have an atmosphere around us, so something that's actually falling in atmosphere, the drag that you might cause, like if anyone's done skydiving, you open up like this, you cause more drag. You actually can slow down or speed up if you come in like this. So I think a little later in the semester, I got a part where I talk about this concept of terminal velocity, where you get going as fast as you're going to get. And there's a difference depending upon whether you have a parachute. Your terminal velocity is much lower than when you don't have a parachute. So that's why we wear a parachute. Look to that. That one's I like. That was fun to come up with. Okay. So, but notice the units on this is kind of weird. It's feet per second. It's not feet per second. That's a unit of speed because we've taken the derivative the units become the units in the denominator become squared. The units in the numerator do not. We're still talking feet, so it's not like area or anything. Okay, just kind of a side point. And we'll just keep moving ahead. That's one example. And the fact that it's negative is, again, indicating direction. We're going down, downward velocity. Okay, and that's the acceleration due to gravity, 32 feet per second, downwards. Okay, so we'll talk about that later on. So now we're going to look at this concept of concavity. Those of you who have contact lenses, you know about concavity, or even our lenses. If you look, there's concavity to lenses, to glasses, and what we call this is, we call this one over here concave up, because it's sort of like this part's pointing upward. And this part here, we would call concave down, because it's sort of, it's pointing. Now, that doesn't really look down, but sort of there, down. It looks to the side, but so you can have a concave up or a concave down. You're putting your contact lenses, you got to make sure your concavity is facing the right direction. Your contact's not upside down, right? And again, we could also say that it would hold water. So, you know, a lot of these were used to, like a quadratic was definitely concave up there, and when it's concave down, it would spill the water. So like a wine glass. So this is the idea of concavity. Notice both of these, if we come from the left to right, both are increasing, but they're increasing at different rates. That's a function of the second derivative. Okay, so first derivative would be positive, because they're both, again, the tangent lines you look are all increasing, going up. So we would see the first derivatives are all positive, but then the second derivative is what we're going to need to use to tell us which one's concave up or down. And here we go. F is considered concave up. That was the previous example. And G is considered concave down. When we talk about its derivatives, just like I said, where the derivative of f is greater than 0, that's telling us that it's going up. And again, on that last graph, both of them had a positive first derivative, but it would be falling wherever the first derivative was negative. Negative is going down, right? But the second derivative is going to tell us the direction of the bend. And there's I come up with a kind of an easy way, at least for me. So when the second derivative is positive, positive makes you smile. What does a smile look like? It looks like that. So it's going to be concave up. And notice that produces a minimum. It produces the bottom of a valley. So we will use a second derivative test. You plug in a value. If the second derivative is positive, we know that it's concave up, like this. It could hold water. We know we're also going to get a minimum. So it's an additional tool in our tool chest. When the second derivative is negative, well, what does a negative look like? Well, negative things make you frown. So it's concave down. Okay. And the slope is decreasing, producing a maximum. So again, we get the top of the mountain. So a negative second derivative means concave down, and that makes for a maximum. Okay. And when the second derivative is 0, that means what would happen from positive to negative. It means we are changing concavity. So we're going from concave up to concave down. That's where the second derivative, f double prime of x, would be equal to 0. And it's what we call an inflection point, or point of inflection. Okay, so that's there. And you can oftentimes see it because you see concavities changing. But to specifically pinpoint it, we've got some mathematical tools now. We take the second derivative, set it equal to 0. We can find exactly where that inflection point is. Incidentally, the inflection point is also the place where you get the greatest rate of change. So notice concave up, the first derivative is going to be, getting steeper, steeper, steeper. And then after that, it gets less steep, less steep, less steep. So this inflection point is also the point of greatest change. So what we do is kind of like what we did with the first derivative, set the first derivative equal to 0. We know we've got either a minimum or maximum. We don't know which one. We just know that there's a minimum or maximum there. Here we set the derivative, the second derivative, equal to 0. And that's when we get that to happen, we know we've got an inflection point. It could also, there's a potential place where the second derivative is not defined. That could also be an inflection point. So it's not always clear cut, but for most of what we'll do, just set it equal to 0. And when you get that, you will have the inflection point. Okay, so something like this, we kind of see it. So we've got concave down on one side where this red is, a pink. We can kind of see visually an inflection point here where it's going to change concavity, and over here. So it does it in two places. And what it's basically saying is a lot of different things, but at x equals 1 and x equals 3, we get points of inflection. Now they didn't give us the function, so we can't actually go through it. We'll do that with other ones though. But this is what graphically an inflection point looks like. Okay. We'd also know on this side, notice we've got the second derivative is always negative, and so we've got the frown. This side it's not as clear, but this is also concave down, which would give us a frown. So here we have the U.S. Consumer Price Index, and so as it goes up, what that does is it tells us about inflation, and so we can see where inflation is the fastest, where it was growing, and again, if we can locate a point of inflection, what we do is we locate the place where the inflation was the quickest or happening the fastest. Back. So eyeballing this, we could say it looks like it could be at what, maybe 5, maybe close to 6. I think I would go. It's kind of always concave up and then it goes back down like that. So it looks pretty close to 6. What we're going to do is using software, this is data points, right? And then what they do is they fit a curve, a function to the data. And they came up with this quadratic, this cubic function here. Okay. If we take the first derivative, we will get the rate of change, and we'll notice that it's wherever it's positive, wherever the first derivative is positive, it's increasing. Where the first derivative is negative, it would be decreasing. Okay, so that's what that tells us. So inflation's going up whenever the first derivative is negative. So we could look at those and again, take the first derivative, the 3 times that, the 2, just take its derivative. And the way to find where's the fastest rate of change, where was it changing, or is kind of in the steepest area, but that's also the inflection point. So one way of finding that, this inflection point, notice it's pretty close to about where they said if we eyeball it. But let's go ahead and go do the math, which is, again, you would have had to take the first derivative. If you go back there, the second derivative, here it is. A lot simpler. It's a linear equation. We can set it equal to 0, solve for that. And what we found was that when x, or t in this case, is equal to 5.8, which is pretty close to 6, that's our inflection point. Okay, so that's where the inflation was the rate of change of the inflation was the fastest. So in the case it's going up, so it was going up the fastest, then it started to slow down. It was still going up, but it slowed the speed with which it was going up. That's what we can use the second derivative for. And it just says, yeah, it was speeding up all the way until t got to 5.8. After 5.8, it's slowing down. That's what the second derivative allows us to see. Okay, and the fastest place was at the point of inflection. Now, the other thing we can use it for, since it does give us concavity, if we take the second derivative, so we took the first derivative, we've got where the first derivative is equal to 0. If we look at that same spot, we can then be able to, maybe we can't get the graph, but we can get whether it's concave up or concave down. Concave up like this or concave down like that. And then that would indicate whether we have a maximum or minimum without ever having to see the graph. So there's instances where that might happen. We're not able to see the graph. Here we can see it. So we can see this one. We do have a maximum here. But what we would see is that also the second derivative, since it's concave down, would be negative. The second derivative over in this point B, all of this stuff would have a negative second derivative. So we're not going to go heavy into it in this section. I think we use it a little bit later, but we can use this second derivative test. Wherever it's positive, that's going to be concave down. Like wherever it's positive, sorry, got to remember, positive is a smile. Draw it, I can see it. Positive is a smile, so we're going to have a minimum because that's the bottom of the valley. If our second derivative is less than 0, which means negative, then we've got a frown, which means we will have a maximum at that value. Okay, and that's pretty much the lesson today. So go into the homework, work through there. You'll be taking second derivatives. When they ask for acceleration, remember, and they give you the position function, remember the second derivative is acceleration. So you'll be able to work through those and it will all be just fine.